Hello, everyone. Welcome. Good to see you again. Welcome again. Today we have class number 8 about binary exploitation and fuzzing, and we already lost the video. Right? I think it's coming. No. Still nothing? I'm trying to unplug. Wait a moment. I think maybe the full screen video broke it. Linux is saving it. It's Debian. Wait, now? It's gonna be there. Yes. Sorry about that. Hopefully that won't happen again. Is the font size all right for you guys? Okay, so let me start again. Welcome at the class number 8. How are you? I hope you are fine. Today it's gonna be fun, very practical, very hands-on, a lot of technical, but it's gonna be fun, I promise. Online people, I hope you can hear me. I hope you can see me. I moved with the computer. Yeah, could be the plug. If there's one. Sorry, let me try to unplug and plug again. Yeah. We are a tape generation. Okay. Maybe just keep it like this. Should I? You can try. Thank you. Okay, welcome. So as I said, today it's going to be about binary exploitation, very technical. It's called the one where we smash the stack, so I hope you are looking forward to it. Before we get to today's class, so again, some organizational stuff in the beginning. So in the document, again, you can see all the important links that you might need for the class, as usual. We have also a feedback from last week. We have 26 responses and 70% that the pace was just right. So it was not bad. 26 responses is all right, but since we have more than 1,000 students registered to this class, it's also not many. So please try to fill the feedback as much as possible because we are actually reading it. And we are trying to react based on it. So this class is going to be a little bit slower, also because it's very technical, and also we take it into consideration for next year. Regarding some Parish notices, I have important note for you guys here, the CTU students who are coming here physically, is that next week the class is moved from this lecture room to the other lecture room with the number 301. It's the one above the buffet, the one a little bit smaller but still big one. We will announce this one more time, I'm sure, during the week in the metrics, so make sure you are reading the announcements channel. Yeah, and it's only one class, it's only next week, and everything else remains working as usual for online people, so there's going to be recording, there's going to be live stream, no changes there. So only if you are coming here physically, next week in another room, okay? Also, for you CTU students, the deadline for the unlock report is approaching, so it's less than a month now, which means if you didn't submit it yet, consider doing it as fast as possible because it's a requirement for you to participate in the bonus assignment, which allows you to skip the exam, which is super good, and we recommend you to try to take and do the bonus assignment because it's basically the same as an exam, but you have like almost 2 weeks to finish the bonus assignment compared to the exam where you have like 3 hours to finish the assignment. So it's much better to try the bonus assignment, and for that you need to submit the unlock report, all right? Also, we have no Pioneer prizes this week because there was no assignment last week. But that means you can catch up with the other assignments if you still didn't solve them yet. That's good news. Also, we fixed the reported bug in SCL because there was a broken sticky vertical divider, so this should be fixed. Thank you for the report. Also, if you find some bug in SCL, please, you can open an issue directly in GitHub. It's going to be much faster. And if you like SCL, consider giving us a star at the GitHub repository. And a final Parish notice is for mock students and people who are using SCL. Please start the class 8 environment probably right now, so you have it ready for the future. It may take up to 5 or even more minutes for start. We don't need it just yet, but so you have it ready. I'm going to do the same. Now it's zoomed in, but if you just open the binary exploitation and you click start. For me, it was quite fast because I already did it and everything is cached, but for you, it might take some time, so please do that. And that is all. Do you have some questions about anything I said? The unlock report, bonus assignment, usual assignments, or anything? Perfect. So we can start with today's topic. As I said, it is going to be about binary exploitation, mostly stack buffer overflow, and we will also touch and write an exploit using return-oriented programming. So most of it will be very technical. We will cover also some theory. It's going to be fun. And at the end of the class, we will cover a little bit of fuzzing. We will see how much time we have. And yes, that's basically the outline. So in the beginning, I prepared for you a small motivational example. It's all just about this small C source code that you can hear. Just let me say that in this lecture, I'm going to assume some knowledge that you guys have. In this case, it's a little bit of C syntax and programming. But if you have any questions, and I'm assuming something you guys don't know, feel free to ask. It's completely fine, and I will happily repeat it or try to explain something that I didn't cover, okay? But mostly we will be working with source codes that are not difficult, small functions, and you will see yourself. So here I have for you prepared a small magic trick. So we have this C code, one function, very small, right? So what it does, there is only 64 bytes long buffer, then we read user input, and then we print the user input back to standard output. Nothing weird, right? Basically, this program is like echo. It echoes everything you put inside, it echoes it out back. At least it looks like that. So let me show you the magic here. You can see I have completely the same C source code that you just saw. Can you see, is the font all right? I have also a makefile that compiles the source code. Very simple makefile, only calling GCC without any special flags, okay? Just producing one compiled binary. So I can run the makefile and produce the binary. See, now I have the binary that I can call, and I can do hello world. It echoes back, so it's doing everything it was supposed to do, right? It's doing hi BSY class, so it's working. Well, and now to the magic. So I have also, if you can see, magic.py script that is doing something. The content of the script is now kind of irrelevant, so let me just show what it does if I run it. The magic Python script, if I run it, it outputs gibberish, something just to the standard output, okay? Some bytes at the end, some weird bytes that are not printable, something weird. So now let's see what happens if I pipe this output into the binary that we just produced. And I'm going to do one more small trick and pipe it like this. I'm going to explain later in the class what I'm doing. Basically, this is only because of standard input and standard output. We want to keep the standard input opened. So let me run this and pipe the gibberish into the binary. And what can I do now? And see, I got shell. Magic, right? That small C source code that is here, I executed it with a special input, and I got fully functional rich shell. I can do networking, I can read files, basically anything. So this is just a motivational example for you guys. I'm not going to explain right now what is happening, because at the end of this class, all of you will be able to write the content of the Python magic script and write the exploit yourself to actually exploit this binary into spawning this shell. All right, so I hope you are motivated, and now to the binary exploitation. Has any one of you have some experience with binary exploitation? For example, playing some capture the flag competitions, or from other course, or doing it in your free time? I see some hands. Yeah, Max also. Quite a lot of hands. That is nice. Does anyone want to try to say us how you would define binary exploitation? We have microphones and cubes, or I can repeat it.
Hi, hi, hi.
Yeah. Anyone? No? Sebas would like to throw something.
I feel like throwing.
Anyone? Anyone?
Okay, it's okay. There's going to be more questions in this lecture that you will be able to answer later. So the definition that we have in the document is that binary exploitation is the act of subverting a compiled application so that it fails in some manner that is advantageous to the exploiter. So important part to take away from this sentence is that we are dealing with compiled applications, all right? There are some applications that we are trying to exploit to our advantage. We are trying to find some unintended behavior in the binaries that will help us to achieve some goal that we have. One other theoretical way how I like to look at it is that if you think about any program or any binary, any application, it can be described as a state machine, right? Maybe you were taught about this in some other course. And each program at some point is at one state, and there are edges leading to other states, right? You can move between states. So when you are exploiting a binary, what you are doing is that you are trying to find edges that were not supposed to be there, some hidden movements from one state to another that is somehow advantageous for you, okay? The team or the people that created the application, they didn't think about this, that you would be able to do this. So you are trying to a little bit think outside the box and outside of the system where the binary is running, and outside of the framework and the compilation, the compiler and everything where the binary is running, the whole stack, you are trying to find some edge from one state to another that will help you achieve your goal, all right? That is basically the theoretical definition of binary exploitation. Of course, in practice, it's very different, sometimes quite difficult, because there are so many scenarios where when you want to exploit a binary, what can happen, right? So for example, what information do you have? So what access do you have? Do you have the binary, like a blob, and you can look at it? Do you also have the source code before it was compiled? Do you know how the source code looks like? Do you know how it was compiled? For example, what compilator was used, and what compilation flags were used, or what framework was used to produce this binary? And then where the binary is actually running, right? Because if you compile a source code at a Windows machine and a Linux machine and a Mac machine, it's always a different binary. And when you want to exploit it, you want to be precise, and you need to be precise. That's why you need to know what is actually running, where is it running, how was it produced. And that's why the level of information that you have in order to exploit a binary, it makes it extremely different every time. Then also, yeah, as I said, the operating systems, right? The architecture of the processors, because when you compile a source code in a Linux machine and there are different processors, the binary will always be different based on the architecture of the hardware, right, of the processor, because there are different instruction sets, and the binary is basically just a set of instructions that are being executed. So they are also different if the processor is different, and you need to know this before you can exploit it.
Can you dismiss this and put bigger than this, like 200?
200?
Yeah, because for people it's a bit too... Okay, like this, maybe?
Okay. I hope better. Okay, and then when you actually maybe know all this information and you decide that you want to exploit some binary, then you have many ways how to exploit it, right? It depends on the vulnerabilities that are present in the binary. So, for example, the famous stack buffer overflow, which will, by the way, be the main focus of us today in this class, where you are overwriting buffers on the stack. Then heap buffer overflow, very similar one, but you are overwriting not stack, but heap. Or, for example, format string bugs, those are also very famous, that you can use to print parts of the running memory, for example, to leak secret values in the memory, such as password and private keys and stuff like that. And also, I would like to say that it's kind of similar to reverse engineering, which will be covered next week by Mari. So stuff that you will learn today is going to be useful for you even for next week. But the difference that I see between reverse engineering and binary exploitation is that in binary exploitation, your goal is to exploit the binary. You don't really care what the binary is about, what are all the features, what is all the code. You have just one goal, you want to exploit it, and maybe you will reverse engineer the binary in order to know how to exploit it. But that's basically your whole goal. But you can use reverse engineering to much more, right? For example, you are reverse engineering a malware, and you want to know everything that the malware does, right? If you are reverse engineering malware and you want to know what the bad guys programmed, you want to know everything, all the features, not only up to a point to be able to exploit it, but to know how it's behaving. So that's how I see the difference between it. So, all right. Now we can move to a little bit of theory. I promise it's not going to be too much, but it's mandatory for us to go over it so you guys understand all the exploits that we are going to be producing today and writing ourselves. Let me just say that if you think that you don't understand what I'm saying, then it's probably because I am not explaining it correctly, all right? It might sound complex or difficult, but it actually is not. So if there is something missing for you and you don't understand it, just please ask me. I will try to explain again or with some different words, and we will see, all right? So as I said, in this class, we will be talking about compiled applications. That's what we mean by binary. We mean something that you can execute and run it. And as I said, it differs a lot based on a lot of factors, such as architectures and operating systems. So that's why we are limiting ourselves in this lecture only on Intel x86 64-bit architectures, all right, and Linux operating systems, which means ELF executables. So if you learn this, it's going to be useful for you even for other architectures because the concepts are extremely similar. But still, this architecture is predominantly used nowadays for server computers. So it's even useful, in my opinion, most useful to learn this architecture at this point. So the first concept that we need to understand is virtual memory. I'm pretty sure you guys maybe know more about virtual memory than I do because you had architecture of computers. It's a long time since I had the class, but can any one of you try to tell us what a virtual memory is? How you would describe virtual memory? Some of you said you have some experience with binary exploitation, so there I see one hand. Oh, maybe wait, Sebas, since he's running. Thank you.
So virtual memory is operating system feature that allows for every process to have basically its own address space, so it doesn't, when the program fails or tries to override some location that could be dangerous, it only does it in its own address space. So it cannot override the memory locations of the operating system and other processes. It's kind of isolation of the process from the rest of the system. So the process only works in its own memory space and doesn't.
Yes, perfect. That's
anywhere.
basically it. Thank you very much for the answer. Sebas has even some candy, I believe. He's not throwing it now, but maybe later. So yeah, let me just comment on this. I think that was a perfect answer. So virtual memory is basically, it's a memory management technique used by modern operating systems, all right? It's an abstraction that applications have on top of your hardware memory that is in the computer. So when you are, for example, working in a C code, you have some pointer, or you see some address in a stack trace when your application crashes, you can see a lot of addresses, right? So what you see is only virtual address. You never see the real address in the memory. So this is the abstraction that operating system does for you. And every process, every program that is running, every executable has its own virtual address space, only for the program itself, all right? One reason is, as our colleague said, is because of the security, also because there's this isolation, right? Because if I have one process that has one address with some data, and I try to access the same address in another process, it won't work because it's completely different addresses. The virtual address space is different for every process, all right? This is important to realize. Then when the program is actually running, the operating system, it translates the virtual address into the physical address. There is some memory management unit, which is a hardware device, but it's not really important for us. For us, it's important that when you have an application which is running, it's using the virtual memory, all right? In the document here, you can see very basic layout of the virtual memory. So every process has this layout of the virtual memory when it's running, all right? And there are some important sections. So there is, for example, the program section at the below, which is the code itself, the binary itself. Then you have a heap. Heap is for your dynamically allocated memory. So, for example, when you use malloc in C code, you allocate space in heap. And then there is stack, which is the most important section for our class today. And stack is for local variables, right? When you look at this diagram, very important thing to realize when you look at it is that the stack is growing downwards, okay? You can see the arrow and the number 000, the address 0 at the bottom. So the stack is growing always downwards, okay? That is one thing to remember, and soon you will realize why. So as I said, stack is very important for us today in this class. Stack is used for mainly for local variables. So in a C code, when you, for example, declare a variable, some integer or some array or whatever, and you don't use malloc, it's a local, those are local variables with a static size, they are put on the stack, all right? And then we have three important registers, processor registers, that are related to the manipulation of the stack, and they are important for our exploitation today, okay? I'm gonna explain just these three that you see here. So first of them is RSP. That is a stack pointer. And the only thing that you need to remember is that stack pointer always points at the top of the stack pointer. So every time when you enter a function, you allocate new space on the stack for local variables, okay? And you need to be somehow able to access these local variables. And you are using relative addressing. That's why you need to know the address of the stack when the function started. That's why we have RBP, okay? Every time when you enter a function, you store to the RBP the current address of top of the stack, so you know where the local variables are stored, all right? And the final register is RIP, which is instruction pointer, very simple one. Basically, RIP always points to the next instruction that is gonna be executed in the binary, okay? So binary is a set of instructions you are executing one by one. So RIP always points to the next instructions that will be executed. So during a normal execution, you execute one binary and increment RIP. You execute instruction and increment RIP. And you are moving instruction one by one using this RIP register, all right? And then, regarding the virtual memory, we have also two important instructions that we need to cover, and it's regarding manipulation with the stack. So I didn't say why stack is called stack. It's because it's a data structure that you might know from programming. It's really stack. It's a last in, first out data structure. So whatever you put in the stack, then when you want to put something out from the stack, you take it from the top. It's basically a stack. And when you implement stack in any programming language, you usually put there two functions as interface, which is push and pop. And that's why you have push and pop as instructions on a processor, which is basically only putting value on the stack or popping value from the stack. For example, if you want to put a new value on the stack and the value is stored in this RDY register, you do a push RDY, which means that value in the RDI will be put on the stack. And this is important, since you put something on the stack, that means you made the stack bigger, right? That's why you need to decrement the RSP register. If you remember, RSP register always points at the top of the stack. And since we put something on the stack, we made it bigger, right? And since stack is growing downwards, that means you need to decrement you need to decrement the RSP register. Make sense? Okay. The equivalent but opposite action is when you want to take something from the stack. It's pop RDY. If you do pop RDY, you just take value from the top of the stack, put it into the RDY register, and you increment RSP. Again, because you took something from the stack, which means you made the stack smaller, and since stack is growing downwards, that means you increment the RSP, because RSP must always point to the end of the stack. Okay, all good? Online people? There is a question?
Just 1 second. Does pop remove, delete a value from the stack?
Yes, exactly. It takes the value from the stack outside the RSP. So RSP always, no matter what happens, RSP always points at the end of the stack. And if you take something from the stack, you made it smaller, so you need to increment the RSP because the stack is growing downwards. I hope that makes sense. It's a little bit confusing because the stack is growing downwards, but you know the heap is growing upwards, so one of them had to grow downwards. Okay, and a final theoretical part before we jump into writing the exploits is just to describe a little bit how you call a function in assembly. And don't worry, this is again not difficult. It's actually very similar to what you would do in any programming language, okay? So when you call a function in a C code, and then you compile this C code into a binary, the compiler preserves this function in the binary. It's just coded in assembly. And in assembly, what you do when you want to call a function, there is a call instruction, And the call instruction has just one argument, which is an address where the function is located. Okay, so for example, this is a calling function at address 123. Here, I have a small diagram to show you what actually happens when you call a function, okay, in assembly. So first, look at the left side, which is the initial state before you call a function, all right? You can see that the instruction pointer, which I said is next instruction that is going to be executed, is the call instruction. And the call instruction wants to call function at address FF120. So what happens, now you can look to the right, to the number 2, is that the address of a function is now in the instruction pointer, okay? Because instruction pointer always points to the next instruction that is going to be executed, so we just put the address of a function which we want to execute. It's like a jump, okay? We jumped by putting the address of a function that we want to execute into the instruction pointer, okay? But also what happened, look at that this address, the red one, that was below the call instruction, that is now on the stack here. See, the RSP register that always points at the end of the stack, it now points below. That means the stack got bigger, which means we put something on the stack, and we put on the stack this value, which is actually the address of a next instruction if we didn't call the function. You see that? Now, why did it happen? Does any one of you know why did we put this address on the stack? Exactly. Let me repeat. It's the return address where we want to return. Thank you. Yeah.
I'm sorry.
It was good.
You want another one?
No, but thank you. That was a perfect answer. So the reason is that if you think about it, when you write any code in any programming language, when you call a function and the function ends, you return back, right? Before you call the function. So you need to somehow remember where you want to return. So the way how it is handled here in x86 assembly is that so you put the next instruction address on the stack. You save it there for you for the future when you want to leave the function, so you can use it again. So you know where to return. All right? No questions online?
No questions.
So and now if we know how to enter a function, now the question is how to leave a function. It's again quite. Oh, sorry. So before, let me just say that if you think about the call instruction, it's just equivalent to these two instructions, right? Because what happens is that you just store for the future on the stack your instruction pointer, which is the return address, and then you jump to the address where the function is. Okay? So you can think about this call instruction as a syntax sugar for just these two instructions. All right, so and now when you are in a function, you also want to leave the function, right? That is also quite simple in assembly. You simply use ret instruction, and that's all. No arguments, just ret. And we can see again the diagram, how it looks. So look at the left side. The next instruction to be executed, because the RIP register is pointing there, is return. And what happened is that we just popped the value from the stack, the return address that we saved there before for us for the future. So we popped it into the instruction pointer. Do you see that? The value we stored there for us for the future, we took it back and put it into the instruction pointer, which means we basically executed the whole function, and now we are resuming executing the instructions that were before, after the call function that we wanted to call. Yeah?
Okay. Ready?
Maybe it's a noob question, but why all the complicating moving around of those instructions from stack to program? Why not just keep them in program and just moving the RIP positioner to where you want?
Sorry, you mean why do we have actually the function then? Why it's not just below the...
In this example, why do we need to put the 0xf-b008 first to the stack in the previous picture, and now we took it back to the program?
Okay, well, because we want to return to the execution point where we were before, right? If you have any program, for example, in C or Python or anywhere, if you execute a function and the function ends, the execution continues at the place where you call the function, right? So you go back.
Oh, okay.
So basically, this is completely the same in assembly. You execute a function, you execute all the instructions in the function, and then you return back to the place where you were before you call the function. So you can continue. Yeah, and for that, in order so you are able to return back, you need to know where to return, right? So what happens here, in this case, in this architecture, is that the return address is stored on the stack for us. So when there's a time to return, we just pop the value from the stack to the instruction pointer, and we are continuing with the execution.
Okay.
Did it make sense?
Yep.
Yeah, thank you. Okay, and now I promise this is the final paragraph from the theory part. So now we know how to call a function, but what about if we want to call a function and pass some arguments, right? Because if you cannot pass arguments, then it's not really useful. So the way how you pass arguments, it's also different based on the architecture of the system. So in this one that we are covering, x86 64 bits, you pass arguments in registers, okay? That means before you execute the call instruction, you just prepare the argument values in the registers, and then the instructions of the function, they use them, okay? So you pass the arguments in registers. That's a difference, for example, from the architecture of x86 32 bits, because at 32-bit architecture, you passed arguments on the stack. Now, because of optimization reasons, you pass them via registers because it's a bit faster. All right, so that's all from the theory. I hope I was clear. Is anything not clear for you guys? This is the core theory that is must-have to understand to do the exploits that we are going to do right now. If there's anything unclear, or I assume some knowledge that you guys didn't have, or you want something to repeat, I'm going to wait 5 seconds because it might be even hard to think about the question.
Any questions from the internet?
Any question for the internet also?
Be sure you get it, huh? Be sure you understand this is the core part of binary exploitation.
Is this going to be on the exam?
Yeah.
Unknown.
Cannot confirm nor deny. Okay, perfect. So we can continue. So as I said, we will be focusing today mostly on stack buffer overflow. So stack buffer overflow, it's quite known and old vulnerability. The first time it was formally described for the public was in 1996, so it's almost 30 years nowadays. And first it was described in the Frag magazine. I put there a link for you, you can open it. You can read the original content, how it was described, how they let me make it bigger for you guys. Actually, all the text in the year 96, how they managed to do the first stack buffer overflow, at least publicly and formally. And if you open it, I recommend you to try to check this magazine also, because it's a really kind of old school one, traditional one, hacking magazine. This is the place how people used to learn stuff back in the days when there was no AI, no Google, no search engines. this is how you passed knowledge to others. So you can see right now there are already 72 editions with a lot of articles about hacking. Sorry?
No internet.
There was no internet, but yeah. I don't know, actually, we can look the first edition, issue number 1, that was released in 1985, okay? So you can try to check some text, some posts about the hacking in 1985. It's a lot. There is a lot of content about phreaking, right? That is controlling the phones via voice. That was very fun hacking techniques back in these days. And we have one specialty for you guys, because we have in physical copy the latest edition of Frag, which is 72. This is when they were 40th anniversary. This is from Eco Party. It is just a different cover. This is the original one from DEF CON that Sebastian and Veronica brought this year. So we have it here for you. You can, during the break, come check it out. But please be very careful, because Sebastian will use his own body to defend it.
And special thanks to Fede from Eco Party that gave us this amazing new FRAC edition, Eco Party edition, to share with you, so you can actually pick at it like printed version. Yeah.
Yeah. Sorry, online people, we don't. But you have the online version there. Okay, so this is origins of stack buffer overflow that we will be exploiting today. So what it is? Stack buffer overflow happens when a program writes data beyond the boundaries of an allocated data structure on the stack. So I already said that stack is used for local variables, all right? And you can put into the local variables user input, right? Maybe you ask a user some number or some text. And if you store it in a local variable, that means you are storing it on the stack, because local variables are living on the stack. But we also saw that we are storing also return address on the stack, right? So we are storing the user input, potentially, and also return addresses. So maybe now you can think about that this sounds a little bit dangerous to do it this way. Now, someone might ask a question whether this is still relevant if it was published first in the year 96. And the unfortunate answer is that yes. The reason is that stack buffer overflow itself, the idea, is not really a bug. It's a feature, or it's an inherent feature of the architecture that we designed. And it's a responsibility of the programmers and the one who codes the applications to not allow this to happen, all right? And just some examples here why this is still relevant nowadays. So for example, in May 2025, there was several stack buffer overflow vulnerabilities in Fortinet products. I don't know if you know Fortinet, but it's a very famous, worldwide known security company with a lot of security products. So they had stack buffer overflow vulnerability in the products that allowed unauthenticated attacker via special HTTP requests to execute remote code, all right? This is extremely dangerous. And the way how the security team of Fortinet discovered this vulnerability was not by accident, it was because they discovered that someone is actively exploiting this. So it's not a theoretical vulnerability, this is actually being exploited in the wild by hackers. And in this case, unfortunately, they discovered it after zero-day exploit was used. There are many other examples. If you just put stack buffer overflow CVE into Google, there's going to be plenty, I would say hundreds or maybe thousands of vulnerabilities. Maybe you can remember the heap buffer overflow vulnerability in 2023, almost 2 years now in curl. That was also quite famous because almost all libraries and frameworks are using the curl library, below. Yeah, and as I said, many other. So the question that I already asked is if we can eradicate this and make sure there are no stack buffer overflows happening again. Unfortunately, not really. We can try to limit it. So we can try to, for example, use memory safe languages, right? Maybe C, any language that doesn't require you, for example, to check for boundaries. But even if you do so, you cannot guarantee there is no bug in the compiler, in the JVM, in the any application that is on the that is in the application stack helping to execute your application, right? Still, at the end of the day, below the binary when you run it, it's still the same architecture that allows this vulnerability to happen. So we cannot really make it disappear. Okay, so almost end of my talking. Now we will finally start writing some exploits, all right? Now I will ask you, all of you, CTU students and mock students, online students also, to connect to a special exploit lab container that we prepared for you. The reason is that for some of the examples, we will use special syscalls that requires some privileges, and that's why you need another container for that. So for online students, you can just, after you started this class environment, you can just SSH to this IP address. The same IP address is used for CTU students. Let me just first connect in SSH. I'm gonna use password admin, and I'm there, okay?
Maybe while we wait, we have some questions. One is, isn't all of this supposed to be prevented by Cherry? I don't know what is Cherry.
Cherry? How was it? It was Max? Can you elaborate? By what, sorry?
Okay.
I'm not familiar with this.
Look into it.
Okay. Thank you.
So the Chariot platform is like a hardware extension which also tracks capabilities for every single pointer. So you cannot dereference any value you wish, and you can track at runtime all the things you would want to do in a memory safe language, except it's now a capability of the hardware.
Honestly, to be completely honest, I hear about this for the first time. I'm pretty sure you should be able to prevent some of it with this approach. But for example, the first exercise that we are going to do right now, that you will see in a couple of minutes, I'm pretty confident that you cannot prevent this, because you are not dereferencing anything. There is no pointer. You are not overwriting anything. It's just because the way how we will exploit, for example, the first exercise could be a legitimate use of the app and of the programming language. In most cases, it's not, but you'll see.
Yeah. So another question is, what is a memory safe language? Can you give an example?
Yeah, so memory safe language, like, for example, Java, Golang, Python, and these kind of languages, where you are not responsible for the memory management as you are, for example, in C language. Or also Rust is memory safe language. Nowadays, it's being claimed like that it's a successor of C language because it basically allows you to do the same. It's being used in Linux kernel, but it's memory safe. That's why we should use it, so we don't have no more stack buffer overflows. So as I said, you can limit it. Probably you yourself won't make a stack buffer overflow if you use memory safe language, but still you cannot guarantee that there is not some bug in the compiler or somewhere on the way that's gonna introduce the bug there. Sorry. Okay, so let me finish the connection to the exploitation lab, because also you CTU students, please connect with this command. You just need to substitute the your number placeholder with your number that you can find here. This is your container. If you type hostname, you can find your number. For me, it's number 5. So I replace the number 5 here. I use the password admin, and I am in the exploitation lab, okay? So make sure all of you, online people, CTU students, everyone is connected to the, na zdraví, to the exploitation lab. Everyone connected? And just please, CTU students, since all of you are sharing one container, please don't try to mess with the container or with your schoolmates, users, or data, okay? Be respectful and mindful in this class. Everyone connected? No issues? Okay, perfect. So let's go into first example, and you guys will write your first exploit. The first example is stored in this path, data binary exploit class stack 0. It's the same for CTU students and mock students. So you can just copy this command, which will copy the files from a read-only directory to your home, so you can actually use it. So you can see there is a make file and a C source code. Here in the document, there is a copy of the same C source code that you have in your exploitation lab. So we can look what it does. So there are 2 local variables, one integer variable called modified, one buffer of characters, which is 64 bytes long, because one character is 1 byte, so this is 64 bytes long. Then we initialize the modified variable to be equal 0. Then we read user input. And then we check if the local modified variable is not 0. And if it's not 0, then we print access granted, and we execute shell. Maybe you don't know this system function. It's a function from standard C library that basically allows you to execute any command. In this command, we want to spawn a shell, right? So it's the reward for us. If we actually print access granted, we should also get a shell. And if we fail, we see access denied. Okay? Very simple C source code. Do we have some questions? Perfect. I said there is also a make file. We have also in the document the content of the make file. Again, you can see simple make file that just compiles the C source code without any GCC special flags, so standard default compilation. So we can use a make command to actually compile the application. Now we have 3 files. We compile the binary. We have the binary called main. And now, so what is wrong with the code? Does anyone know? Oh, yeah. Thank you.
So we don't check the length of the user input or what is loaded by the gets function. So I guess if we load more than 64 bytes, we can modify the modified variable.
Yes, perfect. Thank you. It's perfectly correct. Seba will reward you, I believe. Nice. Yeah, so that was perfectly correct. So the vulnerable part of this code is this line, all right? This is very dangerous to use in the C source code, but it is there, so it can be used. Why not, right? So what this function does is that it's reading user input until it sees a new line. But until it sees a new line, it can be 1,000,000 characters. It doesn't care. But you can see it's putting the input into the buffer variable, but the buffer variable has only 64 bytes. So now there is a question, right, that the curious person should ask: what happens if the input is longer than 64 bytes? There is no place for it on the stack, right? We allocate only 64 bytes. We can look at it here at this diagram, how the stack should look like when we actually initialize the modified variable to be equal 0, okay? So as we said before during the theory, when you enter a function, you store on the stack the return address, right? So that's the one here. You must know where to return, even if it's the main function of C code. So that's the one on the stack. Then we also save alt RBP value, because we need to also preserve it, as I said. So these two addresses, they are almost always there. They are like orchestration kind of values on the stack. And then finally, we have the local variables. Okay, so we have the integer variable, 4 bytes, integer in C. That is this one. We initialize it to the value 0. That's why on the stack we have a value 0. And then we have 64 bytes of the buffer. Okay, this is how we declare the variables in the code, right? First we declare the integer variable and then the buffer. This is in theory how the stack should look like. Do you follow?
Okay, question from the internet. If the buffer is only 64 bytes, why doesn't the input get truncated if it's too long?
Because the programmer, great question, by the way, thank you for that. And the reason is because the programmer didn't think about that. So that's the kind of beauty of the memory unsafe language like C, right? You can do whatever you want. So the programmer, either intentionally or unintentionally, but decided not to check the user input. Usually, you should not write the code like this, and you should use other function to read the user input and specify the maximum number of characters that you allow to be read based on the buffer that you prepared for the input. But this is not the case. For some point, this is written like this. It's a legit and valid C syntax. The function exists, and this is how it's implemented. And also, actually, let me go back here to the code. When we compiled the application using the make command, you can read that there is a warning that says implicit declaration of function. Oh, no, sorry, not that. Here, at the belong. Warning, the gets function is dangerous and shouldn't be used. But still, it is there, and we can use it. So the compiler warns us not to use it, but it's just a warning, and usually it's a technical debt, so who cares about warning, right? As long as it compiles, as it's working, we are good to go. We all know that. It should not be like that, though. Okay, so this is the theory, how we think the stack looks like, right? So let's try if the binary actually works. If I put something, hello, I get access denied. So this is expected, right? Because the modified variable is still 0. I can put whatever. It's still access denied. But this is how we think the stack looks like. And in theory, maybe if we put 64 bytes to fill the buffer and 4 more bytes to override the modified variable, which means in total 68 bytes, we should change the value of the modified variable. Then the code will check that it's not equal to 0, and we won, right? That's the theory. So we can try that. If I execute it, unfortunately, it's not that easy, but we are almost there. So it's not working. Why not, right? So let's explore, and let's try to find out. We will use a GDB, which is a GNU debugger that you can use to debug binaries. You can try to disassemble them. You can try to put breakpoints. You can try to run them. You can try to observe the values of registers and the stack and the heap and everything. It's basically very powerful debugger. So before we start GDB, please open this file with your favorite editor and put there this line, set the disassembly flavor Intel. I already have it there because I already did that, but let me do it again. So what this does is only telling GDB when we will run it that we prefer the Intel syntax for the disassembled code. Okay, it's just a matter of preference. You don't have to do it. The default syntax that you would see is AT-AT, but I don't know why it's the default when most of the people are using Intel, but hey. Okay, so if we save this file, now we can load the binary that we have into GDB. And now we can say disassemble main. We want to see how the main function looks like, okay? What it does. And you can see something like this. I hope you can see it even on the projector. Do you want me to somehow try to change the colors, but I don't know. Yeah, I can do this. So there are a lot of this is basically all the instructions of the main function, okay? And we don't care about most of them, so don't worry. We care mostly only about the header here when the main function starts. And notice this third instruction, this one that I highlighted. What it's doing is that it subtracts from the stack pointer 50 in hexadecimal. If you remember, stack pointer always points at the end of the stack, and the stack pointer grows downwards. That means that if we subtract from the stack pointer, that means we made it bigger, right? If we subtract it from the stack pointer, and the stack is growing downwards, basically we allocated this amount of space on the stack for us to use. Does it make sense? And look at the number. It's a 50 in hexadecimal, which if you convert to decimal, so it's 5 times 16, it's, maybe you don't see it, it's 80. So it's actually 80 bytes are allocated on the stack for local variables, not 68 as we estimated and assumed before. So this is the difference between the theory and practice. The reason is that some architectures, like this one that we are using, they like the stack to be aligned. And in this case, they like the stack to be aligned to 16 bytes. And we thought the stack would be 60, the space for the local variables would be 68 bytes. That's what we tried. But 68 bytes is not divisible by 16. But the closest bigger number divisible by 16 is 80. That's why actually the compiler decided, in this case here, to allocate 80 bytes on the stack. So with this knowledge, we can now leave GDB if you only type Q that exits the GDB. I can go up. Oh no, sorry. Let me clear this. And now we can try to update the exploit that we did before. By the way, sorry, before I didn't explain what we are actually doing with this. So basically, this Python small snippet is just a helper for us to produce the bytes that we want to pipe into the binary, okay? So here we are just saying, okay, Python, I have this code, which is just print character A 80 times, which is 80 bytes. I could put any character. I just put any character because I know a character is 1 byte and I need 80 bytes, so I do just 1 byte times 80. This is the syntax that Python allows me to do. You can see that if I execute only this without the pipe, I get 80 bytes. And now let me pipe it into the binary. Voila, we got access granted. So this means we successfully overrode the modified variable that was on the stack, so it's no longer 0, and that's why we got access granted, even though there was no code that was supposed to be changing this local variable, right? Let me show you again here the code. So the modified variable was not changed, but still we got access granted. Now you might be asking, but our goal was to spawn a shell, right? And we didn't get a shell, we got only access granted. Well, we actually got the shell, but the reason is that since we are piping the characters and the bytes into the binary like this through the Python, we are also closing the standard input. So we spawn the shell and it exits immediately. That's not useful for us, right? That's why there is a small hack that I showed you in the beginning of the class, and we can actually use the cat tool, cat command. Because if you use cat, that you might know that is used to read files, you can actually use it standalone, like this. If I just put cat, it echoes everything that I put inside. If I do hello, 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 BSI class, and see, and the standard input is still opened. That's why I use it here in the exploit that we were writing in the hack like this. That basically, I put our exploit bytes into the cat function that echoes it to the binary, but it keeps the standard input open for us so we can use it, because when we spawn the shell, we want to type some commands, right? So now if I put enter, see, I can still type, and I got shell. Who am I? I got fully functional shell. I can again do whatever.
A comment or question. Maybe it could be interesting to print the value of the variable also. I don't know how or what is meant.
To see, right.
Maybe in GDB, I don't know if you can do it, but...
No, this is a good comment. Yeah, we could do that in theory in GDB. If we put a breakpoint at this point, but it would be, yeah, I think it would take us some time, but this
okay.
is a...
Yeah. It's a good comment, but maybe we can do it in the break, we'll see. Okay.
Yeah. Maybe during the break we can just modify the C source code and show it. That would be the fastest.
So take the time to understand. If you have any questions, be sure that you are doing it, right? That you are exploiting in your computers right now. This is going to get more and more and more complex during the class, okay? We need you to be able to do this in your computers.
Yes.
So if a programmer wants to use this gets buffer or whatever in his library, is there any way to write the buffer in such a way that it expands, how do you call it, by itself, like expands based on the
yeah. So there's always space for the user input, you mean?
Yes.
Well, you can, but you need to implement it.
Sorry, dynamically is the correct word. So dynamically expands.
Well, that's the beauty of some higher level languages, because they do this for you, right? And they do exactly this because they coded it in C or some other low programming language. And they actually do that. They read, for example, only 100 bytes. They store it, and then they allocate new structure for another 100 bytes, and it's going on like this. And you would use because it's dynamic and you don't want the input size of the user, you would use a malloc, and that's why it would not be stored on the stack but on the heap. So there are ways, but it's not out of the blue sky in C. You would need to implement it yourself. Or in C, you should just use other function where you specify the maximum number of bytes allowed, so it fits into your buffer, and that's all.
Okay, thanks.
Thank you. Thanks.
So I have a question about overriding the stack. We can see that we override the values starting from modified and onwards. And my question is, what is the point? When does the operating system actually says, no, you cannot do this anymore? Like, is it when we exceed the virtual memory?
This is excellent question. Thank you for it. And there is just one small exercise right now, and right after it, we go through binary protections that are implemented by operating system and compilers, and I will answer your question. So if you can just wait a little bit, we will go through it. But thank you. That's exactly the right thinking. Like, how can we actually stop this? Okay, so we exploited our first binary, and now you might be asking yourself, like, okay, so what was this like good for anyway, right? Because we already had access to the system. I already had shell. I didn't elevate my privileges. Like, I didn't achieve nothing, right? Well, but think about it. In this case, maybe not. But we already learned about SUID binaries, right? Those are the binaries on the system with SUID bit set on. And when you run them, they are running with privileges of the user who owns the binary. So for example, sudo binary or change password binary. So imagine that this vulnerability is in some SUID binary. That means when you execute it and you spawn this kind of shell, you are suddenly root, even though you should not be root. And now imagine that another scenario, maybe you don't even have access to the system. Maybe the binary is exposed via network socket, and you can only put standard input and see standard output, but you don't have access to the system itself. That means if you exploit it in this way, and you actually spawn the shell, you got access to this remote system that you didn't have before. And that leads us to our other example, which is going to be exercise for you guys that you can individually try to solve, or even you can consult your buddies or schoolmates if you want. It's the C source code that is running in this address. So if I copy it, you can try to look inside, and you will see a C source code that is copied also here in the document. So let's go over it. It's very similar to the previous one, with one difference that there is another function, but otherwise it's completely the same. Okay, so this is the main function. When you run it, there is a function called check password. And what the check password does. So again, there is a local integer variable, 4 bytes as before. Then there is a buffer, which is now 1000 bytes, not 64 bytes like before. Okay. Then we read a user input, again, to this buffer that we have allocated on the stack. And then we compare the user input with some string. This redacted is just a placeholder. Imagine there is some password, something unique that you don't know, okay? So you can try to guess it or brute force it, but probably you won't be successful. You don't know this password. And only if this password, if your password matches the hard-coded one in the binary, then the variable OK is set to 1, and this is the variable that is returned. And then in the main function here, if the result is not equal 1, we again got access granted and we spawn a shell. Otherwise, we got access denied. Okay? So this code compiled with not redacted password, with some unique password, is running at this IP address, 172.20.116 at the TCP port 4444. You can try to connect there with NCAT. I'm going to do the same. And see, I can do hello world. And it says access denied, because I didn't provide the correct password that is in the binary. So as you might already figured out, the binary is vulnerable, almost completely the same as the previous one. And now I'm going to give you 3 to 5 minutes to try to exploit this remotely running binary to spawn a shell. And for mock students, unfortunately, I cannot verify that you successfully hacked into the system, but for you CTU students, I can. So if you manage to spawn a shell, please use the touch command and create a file. Any file can be with your name, or if you want to stay anonymous with anything, but this is as a proof for us that you actually exploited the binary, all right? And again, since this is a shared system, please don't delete and mess with it there. You can verify that it's a fully functional, rich system, but please don't destroy it. Okay, so now I'm going to give you 3 to 5 minutes, and I'm going to connect myself to the system where the binary is running to see if some of you actually hacked inside, okay? Ah, somebody did already. Here I can see user 63. Who was it? Does anyone want a candy? Seba, it's a very nice throw for you. We got 2 more. Okay, so you're fast. I'm going to give you some more time for all of you to try to figure it out. Maybe you notice there's a solution in the document, but please first try to solve it yourself. Try to think about it. How is the binary different from the one we exploited before? Now here you can see the beauty that even if it's a binary, it could be running on a different system. And if you exploit it, you get access that you didn't have before. Moriarty, nice. Online people, all good? Did you manage to hack this remote system? Yeah, for you. Come on, couple more. So we have 2, 4, 6 people.
For people on the internet that they don't have a route to host, you have to start the class 8. Otherwise, you will not be able to reach that, okay?
Yeah, so please, in STL, start the class number 8. And for all the exercises we are doing today, make sure you are always connected to the exploitation lab. There are instructions in the document. It's just one SSH with the password admin. Okay, we got more files. I don't know if those are different users and different students, but hey. Okay, thank you. So let me try to show you how I would solve this, and then we can have a little break. So if you look at the source code, the check password function is very similar to before, right? So there is the variable that we want to override, and there is a local buffer with a static size. Just in this case, the size is 1000. So naive approach would be that I'm going to put 1000 plus 4 bytes, because of the integer is 4 bytes, right? That is 1004 bytes. And we can actually try that. Here I can do Python, and that I want to produce 1004 that is divisible by 16 is 1004. I didn't calculate it in my head. I have it prepared, so don't worry. But if I do 1004 and get a reminder of division by 60, 68, sorry. 68? No. Here. No, I'm doing something wrong. It is 16. Yeah. Thank you. 16. Yeah, it needs to be aligned to 16 bytes. Sorry. Thank you. So you can see that 1008, if I divide it by 16, I get a reminder 0. So that is a nice alignment. And if I actually change our exploit, I got something wrong. What is there? Let me try to use the hidden solution. Maybe I did a typo in right. I didn't put the cat. Here I can put the cat as before. Now access granted, and I can do ls. Oh, and I can see many more files that you guys did there. So thank you. And this is how I would get inside. Here in this hidden solution, if you highlight this section, you can read again even the reasoning why it was 1008 characters. Okay, so let's have a first break. And see you in 10 minutes. Oh, but before we get to the break, one more thing. Let me show a special code for mock students right now, so I don't forget it later. And I should... You cannot? It's fish jink, I believe. Fish jink. I would not bet on that, but... But don't worry, even if you have a small typo in submission of these codes, it's still fine.
We are rewriting, we will be improving this, so it's not that difficult. But this one is from the old one, so please bear with us. Yeah.
Okay, so we can have a small break, 10 minutes. Let's continue at 16:02. Okay. Yes. So can we continue, guys? It's about time.
Okay, until people get their seats, we have 2 questions from the internet. Do you want to go?
Yeah.
Okay.
Thank you.
So the first one is that for someone, he didn't need to put 1008, but he used 1005, and it still worked for the exploit.
Okay, guys, can we continue? So the question from the internet is that we don't really need to in this last exploit that you guys did. Oh, sorry, I scrolled down. Let me go back where we ended. Okay, so we ended here. This is the hidden solution. And what we did is we put 1008 bytes. And the question from the internet is that we don't need to put 1008, and we can put 1005, and it will still work. Well, that is true. And you can try to put like even more bytes or less bytes to see what is happening. And the reason is that the integer variable that we are overwriting is 4 bytes, right? So even if you overwrite just 1 byte of the integer variable, the integer then won't be 0, and the check will pass, and we are in. That's why you don't really need to put 1008. You can put even less, and it will still work. But you can try to put 2000 instead of 1008 and see what will happen. And the second question?
Yes. So while I do understand that we are learning about it, is there a reason today why a binary would use gets instead of fgets, which is the safe alternative? And also, are there other functions that would do something similar with memory buffers these days that are exploitable, and or are they replaced, or yeah?
Yeah, that's a good question. So I don't see a valid reason in any code where you would use the gets function instead of the gets function. Yeah?
I have one that is, this is because you are taking decisions now, but there is a lot of legacy code, especially in all IoT and router devices, that because it's extremely much faster and less using memory, they're still using gets, unfortunately. Not so much, right? But
okay, so yeah, that's one reason. And the other thing to think about, that even if you use the safe gets fgets or getsn function to read just an arbitrary number of bytes, then you need to implement this, right? And maybe you are reading a lot of user input, and you need to implement this logic, and maybe you are dynamically changing the size of the buffers that you are reading from the user input, and you can have a bug in this, right? And then even if you use the safe function, you can still have this bug there because of some other programming bug that you introduced in your own logic. So this is just present in this low-level language such as C, and you always need to think about this.
Of course, here we are using it because it's easier for teaching, right? But I have 2 more things in mind. One is that some libraries include gets for backward compatibility. So it's still there, even though you should not use it. And the other one is like, I hope not, but maybe some LLM coders are suggesting these gets. I hope not, right? But I mean, maybe. Depends which one you use.
Yeah, I would bet my money that some of them are. And yeah, so, and the question was also, is there some other kind of this famous memory unsafe function? So let's, for example, take the printf function, right? That is used everywhere, it's a standard, and if attacker controls the formatting string that is specifying what should be printed, then they can dump the whole memory because of putting some formatting strings into the format. That is just one example that there are many, many dangerous functions if you don't handle them correctly. Okay, so we can continue with binary protections. And this is a nice follow-up for one of the questions we heard here. Like, if there is at least some protection that is defending us against these type of attacks and these vulnerabilities, right? Because so far what we saw, you could think of that maybe you can now go to GitHub and search for every occurrence of gets function and now start exploiting everything, right? It's not that easy in the wild, even though you could do this, and this would be very nice research, I believe. And it's not that easy because there are some protections coming from the either compiler or the operating system or the architectures itself. So let's go through some of them. The most important one is for sure the ASLR, which stands for Address Space Layout Randomization. So this is a feature of operating system, and what it means is that if it's present, and nowadays it's supported by almost all modern operating systems, so if it's there, when you run a binary, then every time the sections in the virtual memory start at a different random offset. Okay, so the virtual memory is always different. When you run the binary once and you print the address of some variable, it's going to be different when you run the binary second time and third time and fourth time. Every time it's going to be a different address. This is because of the address space layout randomization. And thanks to this, the attackers, they cannot assume where something is present in the virtual memory. All right, so if this was not the case, then the attacker would know, okay, I know that this variable is always at this address, so I can use it in my exploit, for example, for something, in some advanced exploit. But thanks to this, since everything is always randomized, you cannot do this assumption, you as an attacker. However, you can still bypass this, right? Because once you start the binary, the virtual address space is somehow randomized, but then it exists and it stays like this. So if the attacker is able to actually dump part of the memory, he learns about the addresses, right? He knows where it lives in the binary. So if the attacker can actually dump these addresses without crashing the binary, and the binary keeps running, then he bypassed this ASLR, right? Because he learned about the addresses. Second protection, we have a PI, which is the position-independent executables. And that is a feature kind of compiler, because when you compile a binary, the modern compilers, what they do is that they compile the binary in a way that the binary doesn't care where it's loaded in the virtual memory. It can be loaded anywhere. And the ASLR that we just described, it uses this and puts the binary somewhere in the virtual address space. Again, for the same reason that later the attacker cannot assume where, for example, the addresses of functions or some constants are in the virtual address space. Similarly as ASLR, as I just said, this can be also bypassed, right? Again, if the attacker is able to dump parts of the running binary, then he learns where the functions and constants are actually exactly living, right? What is the address of some local functions? He can learn this if he can dump the memory. And then one very nice and famous protection, which kind of answers the question we had, like, if the attacker can just keep filling the buffer and overwriting the values, usually he cannot, and it's thanks to the stack canaries. Stack canaries, it's a feature that if it's enabled in the binary, then when you start the binary, one secret value is generated. Every time you start a binary, a new secret canary is generated. And every time you enter a function, this canary is put on the stack right after the return address, which means that if later some attacker tried to overwrite the return address, he was smashing the stack. So the attacker for sure during this process must have overwrote also the stack canary value. Otherwise, he would not overwrite the return address, right? Because the stack canary kind of lies before the return address. And then when the function returns, what is happening is that the binary checks whether this value on the stack, this canary value, is still the same, if it wasn't changed. And if it was changed, then something weird happened, someone is smashing the stack, or there is some bug, and it terminates immediately, the application. And the attacker cannot continue because the application crashed, basically. This is nice. Again, this can be bypassed, right? Because imagine that, again, attacker can, because of some other bug, dump parts of the running memory, and he can dump the value of the stack canary. Then when the attacker in some advanced exploit is actually overwriting the buffer on the stack and the return address and everything, he can overwrite it precisely in a way that he overwrites the stack value with the correct stack value. He doesn't overwrite it. He puts the correct value there. That means later, when the binary checks whether someone was tampering with the stack, the value is correct. So it was bypassed, right? Also, what I learned, and I didn't know about this, is that even nowadays the stack canaries are not by default in the binaries if you compile it with, for example, using GCC in Debian. Because every, for example, Linux distribution, they change the default compiler's installation, such as, for example, GCC, to either put some flags or not. And in Debian, they decided that if you compile a binary with only GCC, without any special flags, the stack canaries are not present. Which is different, for example, to Ubuntu, that when you compile with completely the same way, a binary on Ubuntu using GCC, you will have a stack canaries over there. So even these small details, such as on what system it was compiled, even though the command to compile the application was the same, the binary is different, right? Once there are stack canaries, and the other time they are not there. All clear? Did it answer the question? Perfect. OK, so one last protection that I mentioned is here a non-executable stack. This is a protection against a very nice attack also, because imagine that what we did is that we overrode the buffer on the stack only with random characters, right? It was character A. But imagine that we put code on the stack. We put instructions on the stack. Because if something is data or instruction, it's just a matter of interpretation, right? If I give you one number, it can be a number or it can be an instruction, because everything in a computer is binary. So everything is a number. So imagine that we don't override the stack with random characters, but we overwrite it with code. And then we change the return address to jump on this code that we injected onto the stack. That means we are executing our own code, right? But there is a protection against this that basically flags the stack as non-executable. So later when you try, if you would attempt this attack and you try to jump on the stack, when processor does the instruction fetch in the stack, it would say, no, this is not executable, I'm not jumping there, I'm not taking this instruction, and the application crashes. So this is, again, a protection that you can enable with GCC when you compile your application. But again, it's not bulletproof, right? Because this is just a flag, and the flag can be changed. And there is a special syscall in x86 computers that can either add this flag or remove this flag. So if the attacker is skillful enough and the exploit is advanced, he can just remove this flag and later put shell or any code into the stack, jump there, and execute it. Did it make sense? No internet, no question? Perfect. By the way, now I just described to you how you can inject the code onto the stack and then jump there. Feel free to check this link, which is actually a database of shell codes. If you are, for example, trying to achieve this attack, so you might need the instructions that you actually put on the stack and then jump there, right? So this is a database. I can go there. This is a database of these instructions that do basically anything in any architecture that you can think of. So for example, here we have Linux is 8664. This is ours. Here we would choose, okay, so do we want to do a reverse shell, or do we want to read etc password, or do we want to start just bin shell? It gives you basically the data that you put onto the stack, then you jump there, and voila, you executed any code you wanted. Of course, assuming that the stack is executable, because maybe you made it executable, or the binary has this flaw inside. Okay, so now let's try to actually practically see what I just said. We can try to see these protections on a binary using a checksec tool, like this. You can try to run it, for example, like this. If you execute this command, you can see that it's going to change directory to the stack 0. That's the first example we did. And use the binary that we compiled there to see what are the protections there. Okay, so make sure you are still in the exploitation lab, okay, everyone, CTU and mock students. And if I start the command, oh sorry, it's just because I have it zoomed in, then the format is kind of broken. It should be just one line, but if you execute it, you should see it nicely. What you can see here, and if you remember, we compiled, I can try to see the makefile. This is how we compiled it, right? We compiled it without any special flags, only GCC. And for some reason, oh, never mind. No special flags. And the binary has no canaries inside. See, it's red. That means it's something to look at. Then we can see that it has non-executable stack, and that the position-independent executable is enabled. Sorry, now I have frozen terminal for some reason. Let me try to, I don't know, let me try to reconnect. Okay, so I'm back in the exploitation lab. I'm going to close that one. Okay, so and now let's see a demo that I prepared for you. Try to copy a new files from this path into your home and go there. Over there, you can see one makefile and one C code. It's just a demonstration. It's a very simple one. This is the C source code. One function. There are two functions, but one is used. So we have a main function and a local integer variable. And then we print address of the variable, which is called stack var because it's on the stack, as we already know. Then we print address of a foo function. This is our function over here. Okay, so it's our local function. And then we print function called system, which is not our function. It's a function of, because we didn't define it, it's a function from the standard C library. Okay, so it's a function from a shared library that is dynamically loaded when you run the application. So we just print these three variables. The addresses should be pointing somewhere in the virtual memory, right? And each should be pointing somewhere else because the first one is living on the stack. Foo function, it's our function that is living inside our binary. And the system function, that's a dynamically loaded shared library that's also living in a different segment in a virtual memory. Now let's see the make file. So the make file has two jobs, I believe it is called in makefile. One normal and one NoPy. The normal one, no special flags of GCC, we just compile the application. And the NoPy, we just add the NoPy flag, which we saw in the couple minutes ago. We are basically saying that we doesn't want this binary to be position independentable, okay? That means that basically every time the binary is run, it should be always loaded to the same address, okay? It doesn't support being loaded anywhere. So let's try to compile it using the make program. And now you can see we have two binaries as expected, main and main NoPy. Let's try to run the first one. And we will be running it using the watch command. I don't know if you know it. Basically what it does is that you give it a command, and it periodically executes the command you give it. And in this case, because we put option and 1, it's going to re-execute the command every second. Okay, so we can monitor the output. So let's try to run it. See, in the upper right corner, you can see that it's re-executed every second. And in the middle, you can see the output that it's producing. So you can see that everything is changing. Every time I run the application, all the addresses are different. So if I were the attacker, it's very difficult to assume anything, right? Like, if I want to guess where the foo function or libc or local variable will be located in the next run, I don't know, because every time it's somewhere else. And this is because of the ASLR, the address space layout randomization. This is a feature of the operating system, and it's doing it for us. It's actually trying to protect us against the attacks that I was showing before. Do you have the same results? All good? So now let's try to do the same, but run the second binary that we compiled with the flag that it's not position independentable. That means it always must be loaded at the same address in the memory, okay? So see, so now only address of a foo function, which is our local function, is static. Everything else is still dynamic. So because we told our binary that the binary itself cannot be loaded anywhere, but everything else still can. Everything else is still random because of the ASLR, because of the operating system. So the operating system still puts the stack on a random place and still loads the shared libraries and the system function to a random place. But our function and our constants and our static variables in our own binary, that cannot be random anymore, okay? That's why it's not changing. All good? Do you understand why it's not changing? Okay, and the last example is that we can actually try to disable the ASLR. It's done with the personality syscall, which we can do with this command. If you do set architecture and option R, it basically runs any command that you give it without the ASLR. And this is a privileged action, and you would not be able to run this command in your containers. That's why we are running this in the exploitation lab. Okay, see? Now the time is changing, but nothing is happening. So this is if the operating system didn't try to protect you using the ASLR, this is how it would look every time. And the attacker could assume and would know and would predict where everything is located in the binary and would be able to exploit it. That's why we have ASLR in most modern operating systems nowadays. Of course, there can be a bug in the ASLR, right? It happened. For example, we know computers are not completely random. They are deterministic. You need to have some random oracle to produce random numbers. So how can you even guarantee that the randomization is correct, right? And it happened in the history that this calculation and this randomization of the virtual address was predictable, and attackers exploited it. So that's what I was saying, that you need to account for the whole technical stack upon which your application is running, and maybe everything needs to be safe, so your application program is also safe. All clear? Did it make sense? By the way, small disclaimer, unfortunately this example might not be working correctly for mock students. If you have other computer than x86, such as for example the ARM Mac processors, the reason is that since the containers are running it in x86 mode, so there must be some emulation. It's a QEMU emulation, because still the hardware is ARM. And the emulation doesn't have support for all syscalls. So this syscall, where we actually disable the ASLR, it's not present. And that's why you cannot run this. And there might be even inconsistencies with what you just saw in the previous examples if you are running it in SCL in ARM processors. So sorry for that, but this is, we cannot unfortunately do anything about it. So what is the conclusion of this? Is that there are protections, there are a lot of protections, but all of them can be bypassed. And all of them were proven in the history to be really bypassed and exploited by attackers in the wild. So it's not that academia, theoretical warning. It's real and it's happening, and advanced exploits are actually bypassing all these protections. And it's beautiful. Yeah, so never rely on system protections, and you need to write a secure code, okay? That's the only way how to defend against this. Okay, so again, end of this small theory window. Let's go hacking again. Another example. So please, again, all of you, make sure you are still connected to the exploitation lab, and copy to your home new program that is living in this directory called stack1. Let's move there. Now in here, you can see 3 files, some C source code, make file, and some Python code. First, let's look at the source code. Again, you have a copy in the document. So in the main function, you declare a local variable, which is called fp. I can tell you it's a shortcut for function pointer. Okay, and the value of the pointer points to function failure, which prints access denied. So that's bad. Then we have again a buffer. We are reading into the buffer, again with the gets dangerous function. And then we execute the variable that we have here. I mean the function that we have stored in the local variable. That's all. So again, our goal is to execute access granted and print the shell, sorry, not print, spawn shell. There is again a make file present. You can check it out. Now we have there NoPy option, so we want to compile the application to be not position independent, okay? I can try to run it. It works. See, I have produced a binary called main. Then also in the three files, you had one that was called exploit.py. It's a Python script that looks like this. It's a template for you to write your exploit, because before all our exploits were just one-liners, right? We just printed some characters, we put it inside, and that was it. But now it's getting a little bit more complex. That's why, just so everything is clear and you can reuse it and you can debug it, we are putting it into its own script. So we will use Python. And the way how it works is that we just prepare some buffer. At the end, we print it to standard output, okay? And we pipe it to the binary again. But we need to figure out what we need to print in order to successfully exploit the binary. And right now, it's almost ready for you if you look at it. So the template, what it has is that first in the buffer, we put, again, some characters. Doesn't really matter. In this case, character A, 1 byte. And we put this number of them, buffer size -8. And then we use a struct pack on the function address. So what struct pack does is that it handles for us let me say it differently. We want to override the local variable, the FP, with the success function, right? As before, we were overwriting the local buffer and then the modified integer variable. In this case, it's the same. Just the variable that we want to overwrite, it's not integer. It's actually a pointer to a memory, right? So we need to put the correct pointer of the function that we want to call. We don't want to call failure. We want to call success. So we need to find address of success function and put it here instead of the failure. So later, when it's called in here, we got access granted and we spawn a shell. Did it make sense? Thanks. So I see some nodding. Who doesn't understand? I know, I mean, who understands? Perfect, thank you. Yeah, so that's basically it. And since we are putting the function address that we want to overwrite, we need to put it into a correct format, right? Maybe you heard about that some computers have architecture like big endian or little endian. It basically means when you have a multi-byte data and you are putting it into memory, if you first put the most significant byte or least significant byte and in what order and stuff like this. So you would need to think about it, but in this case we don't, because the struct.pack function does this for us. So we are saying format Q. So we are saying, okay, we want you to format this address, whatever it is, to be 8 bytes, because we are at a 64 bits computer, so 8 bytes. That's hidden in the Q format. And I want you to use the computer native endianness. So it will figure it out for us. We don't really need to care about it. But if you want to know what your computer, if it's a big endian or little endian, you can use this command. Let me try to run it. And you can see that, for example, the one we are using, so it's little endian. But it's fine because the struct.pack will handle this for us. Okay, so to finish this exploit, you can see there are 2 change me variables. We need to find only those. So we need to know how big the filler should be. We need to fill the buffer, right? And then we need to override the function pointer. So we need these 2 values. Let's try to find them in GDB again. Let me clear this. We have it already compiled. It's called main. I open GDB. And what I do, I simply write p_success, which is print information about success symbol, in this case, success function. And it gave us the address. This is basically all. Now we know where the success function is in the binary, and we can use it in the exploit. Okay? And the last stuff, we want to know how many bytes we need to put there to actually override the whole allocated section on the stack for the local variables, right? And we already did that before. You can use disassemble main in the GDB. And as before, you can see here that for local variables, we have 50 in hexadecimals bytes allocated for the local variables. And 50 in hexadecimal is 80. So in total, we have 80 bytes prepared on the stack for local variables, okay? And that's basically everything we need to finish the exploit. So let me finish the GDB. I open the template. And we just learned that on the stack, we have allocated 50 in hexadecimal bytes. That's why I put 50. And we also found the address of the function, right? It's written in the document, and you can also see it in the screenshot. You should see the same address when you do print success in GDB. So I put it into the exploit. And now that's basically all, because if you look at it, what's putting into the buffer. So into the buffer, we are putting buffer size minus 8 characters. So that means bytes, okay? Why are we doing minus 8? Anyone? Oh, you have a, okay. Yes, exactly, thank you. So just let me to repeat, that's where the function goes. So if we would put buffer size number of bytes, we would fill the whole stack space for the local variables, right? But we don't want that. We want to fill everything except the local function variable, which we want to override, and that is 8 bytes. So that's why we put some random characters, in this case, capital A, and then we put the 8 bytes, which is the function address. Make sense? Okay, I see some nodding, thank you. So that's basically it. Now we can try to run it again in the same way how we ran the previous exploits. Let's see, and I see access granted, and I have a shell. Woo! Did it work for you? Okay, awesome. Yeah. Any questions? Yeah?
I have a question about the -8. I would expect that we want to override the whole buffer, so 80 bytes.
Yes.
And then we want to also override the function pointer, so another 8 bytes.
Actually, the buffer is not 80 bytes. Because the buffer, if you look, wait here, let me get the source code. Sorry, no, he had a cube, so it's all good. So the buffer is 64 bytes, but compiler decided to allocate on the stack 80 bytes for us because it needs to be aligned to 16, as we said. So in 80 bytes, you can fit this whole buffer and 8 bytes for the pointer. So the whole stack for local variables has reserved 80 bytes, but only 64 is for this buffer. And then the rest is, one part is not used, and the leftover is used for this one. So that's why we basically filled the whole reserved space on the stack, -8, because that's where the function address goes.
So the 80 bytes is not just for the buffer, but
no,
for the whole stack?
Yes, exactly. It's for all the local variables,
okay.
And in this case, it's just these two.
Okay.
Yeah. Thank you for the question. Okay, perfect. So that was our third exploit. So let's move on. Even on time, so that's perfect. Okay, let's continue with another example. Now it's going to be even more fun. Again, make sure you are still connected, all of you, to the exploit lab, and copy this source code called stack2. Yes.
Quick question, but 64 is also a multiplier of 16.
It is, but you cannot. It is true, but you would not fit there the function pointer, right? So you need to allocate space on the stack for all local variables, which is the 64 bytes buffer, but also the other variable, which was a function pointer, which is 8 bytes. So in total, you need 72 bytes, but that's not divisible. That's not a multiple of 16, but the closest multiple of 16 is 80. So that's why there is 80. I hope that answered the question. And we can move to the next example. It's quite a small one now. You can check the source code again. I'm going to show the document version one. It's the same one. Very simple one. Now we have only one local variable. It's a buffer with 64 bytes. Again, we use the dangerous gets function to read user input. And then there is a function that prints access granted. So our task is to print the access granted, or to call the success function, which prints the access granted string. Again, we have a make file there that we can use. You can type make. That will compile the application for you. And notice that we are compiling it with F no stack protector. So that's a GCC option that I was showing before that says to the compiler, do not put stack canaries there. It's there just so you can see it, but we didn't need to put it here because as showed you in Debian, if you compile C code with GCC without any flags, the stack canaries are not there. So they would not be there even if we didn't put it here. But I'm trying to make it more explicit that the stack canaries are not there, because what we will try to do is, in this case, we will try to override the return address that is usually protected by stack canaries if it's there. So let's look at this diagram again. This is how the stack should look like when we are in the function, okay? As before, as we saw before, first on the stack we have a return address. This is the return value where the binary will jump after the main function finishes. Then we have stored the old RBP value, just so it's preserved. And then we have space for the local variables. In this case, it was only one local variable that was a 64 bytes long array, okay? So if you look at this, maybe you already have an idea like what to do, right? What will be our goal? How do we manage to call the success function? Does anyone want to guess? Yeah? But yeah, where onto the buffer?
Like onto the RBP value, like the return value should be the value of the function that we want to execute.
Yes, exactly. Thank you. So not the RBP value, but the return address, which is those are on a different position on the stack. But you are correct. We are trying on the stack. On the stack. So we know it's there because we just learned it today. So we will try to find what is the address of this function, the success that we want to call, and put it instead of the return address, okay? Again, we have there a template which is exploit.py, Python source code that we just need to fill. Now it's a little bit less. There is less code for us. We need to write more, but at least we learn. So what do we need, right? We need to, again, fill some bytes and then override the return address with the success function, correct? So for that, we, again, need to know the address of a success function. We can do it the same way as we did before with GDB. So make sure it's compiled, that you executed make before. Now load the binary into GDB and run psuccess. And again, this is the address of the success function that we will use, okay? So make sure you save it for later. I'm gonna, I have it here. And now the question is how many bytes we should put again, right? To fill the whole buffer so we can overwrite the main return address. Again, we can do it as before. You just type disassemble main. By the way, in GDB, you can use tab for auto-completion of commands. It's pretty nice. So you can just put disassemble main. It also suggests you name of functions that are present in the binary. So if I do this, and we are interested again only in the size of space allocated for our local variables, right? Even as we did before. So we can see that we subtract from RSP 40 in hexadecimal. So 40 in hexadecimal is, if we do 4 times 16, that's 64, okay? So we have 64 bytes reserved on the stack for local variables, which makes sense, right? Because the C source code has only one variable, and that is 65 bytes long buffer. And not 65, I mean 64. And 64 is already multiple of 16. So what compiler did, it decided to allocate 64 bytes on the stack for local variables, which we need to overwrite, so we can overwrite the return address. Did it make sense? I feel like I kind of said it maybe not very clearly. Okay, let's try to write together the exploit, and hopefully it will be more clear. So this is the stuff that we need to fill, okay? Again, we have some size. It's a size of the reserved space on the stack for local variables, okay? And we just saw that it was 40 in hexadecimal, so it was 64 bytes, okay? We saw it when we disassembled main. We also printed the address of the success function. It's in the document, so I'm going to just copy it. So let me put it here. And now we just want to print it, okay? So what we do is that we need to print size number of bytes to fill the whole space allocated for local variables, okay? That is 40 in hexadecimals. Let's see it here in the diagram. So we need to fill this whole buffer, space reserved for local variables, which is 64 bytes. So that's what we already have there. Then we need to overwrite this RBP value. We don't really care about the old RBP value. It's some value that was there on the stack. It's not important for us right now. So what I can do is that I can do just size plus 8, because the old RBP value has 8 bytes. And now I can just put the return address to the final slot. Okay? Are you following? Basically, I am slowly writing the same exploit that you can already see in the document, so you can see the thinking process behind writing it. And now let's just put the function. So I will add to it, and I will again use the struct.peg, so I don't need to care about the Indianness. It will do it for me, like this. If I didn't make any mistakes, since I wrote it now manually by myself, this should work, right? At least in theory, what we saw in the diagram, because first we overwrite the whole stack reserved for local variables, that is 64 bytes. Then we overwrite RBP value, which is 8 bytes. And then we overwrite the return address, which is the address of a success function that we printed in GDB. Okay? So let's try to run this. Ta-da! We have access granted. Of course, we have also segmentation fault. Yeah, that's That's life. In this case, we were interested in calling access granted, which we achieved, so we exploited the binary for our goal. And the binary didn't finish successfully because we smashed the stack completely. It couldn't continue, so it's exported afterwards. We don't really care. We printed access granted. That was our goal. Did it work for you? No questions? Okay, so we are approaching to second break, and just on time. That's perfect. And before we get to the second break, just a small recap. So what we learned up until now, because we will need it for the final part, which is the return-oriented programming that comes after the second break. So we understood that we put some user input onto the stack, but there is also a return address on the stack. So we can override the return address and basically jump anywhere we want. We can execute any function we want, right? We proved it. We just jumped to a success function. But there is one drawback, and that is that the success function, it didn't accept any arguments. It was plain success function. And maybe we want to jump to a function that accepts some arguments, right? It's doing something more advanced because we want to exploit it properly. We have some goal that requires to call a function with arguments. So we are not able to do it right now. So that's just for you to think about it, how you would maybe try to achieve this. And a small brain food for you to think about during a break, if you want, is that so far we overrode the return address in this example that we just had. We overrode the return address with the address of a success function. But what if we override the return address with address of a return instruction? Okay, so this is maybe a little bit difficult to comprehend in the beginning. Just try to think about it if you want during the break. This is kind of the general idea that we will be using in the return-oriented programming. Okay, so see you in...
Question.
Yeah?
If I get a segmentation fault but without access granted, did I still get in or not?
No, probably not. It depends, of course, on the exercise. And if it's, for example, you are running it locally or remotely, if you are reading for example, output through the network correctly, but in this case you should see access granted. So probably there was something wrong. Try to recompile again the binary and maybe try to copy paste or compare the exploit that is in the document with what you produced, and there should be some inconsistency probably. You should see access granted. Okay, so see you guys in 10 minutes, in 5 minutes after 5 p.m. Okay, so we can continue. Final part, guys, of this awesome lecture. Yeah, internet. Hello. Let's
Come
continue.
back, internet.
I know it's late and you might be tired, but please just try to bear with me for a little while, because this is the final boss of this lecture, and it's a return-oriented programming, and we will write actual exploit using return-oriented programming, okay? So I will try to make it as a story, kind of build up the knowledge what we want to achieve and how we will try to achieve that, okay? So first, again, a little bit of motivation that kind of relates to the recap we did a couple minutes ago. So far, what we learned is that we can override the return address with any function we want. But what if the target function that we want to call accepts some arguments? We cannot do that, right, at this moment, because what I said before in the theory section, if you remember, function arguments are passed in registers. and we don't control registers. We control only values on the stack, right? There is only user input that we control, and that is put on the stack. So we control stack, but not registers. But we need to control registers in order to call functions with arguments. That means that before we actually jump to a function that accepts arguments, we need to prepare the arguments somehow. We need to put them into the registers, because when we actually call the function expects the arguments to be in the registers. So we need to put them there somehow. And to do that, we use ROP, return-oriented programming, which is a super nice technique. We have a definition here that leverages the existing code in a binary to run a specially crafted series of instructions to the attacker's advantage. Okay, so again, we are trying to exploit the binary to our advantage. And we will do that by running specially crafted instructions that are already present in the binary. We will just try to chain them together to do a functionality that we want to do. In this case, it is to prepare the value of the arguments in the registers so we can call a function, okay? Now, important term to know in return-oriented programming is a gadget. So we will be chaining together gadgets, and each gadget is a series of instructions that do something for us, what we want to do. And usually they end with a return instruction. So for example, here in the document, you can see one example of a gadget. Okay, so for example, this is a gadget which has two instructions. First instruction is pop RDY. That means we are reading value from the stack into the RDY register and then returning. Okay, just a series of instructions. Think about that if we somehow manage to run this, that means we prepared the argument in the register. Because if you remember from the theory, arguments of functions are passed in registers, and the first argument is always passed in the RDY register. So if we somehow execute the pop RDY, and we prepare the value on the stack that is being popped into the register, that means we prepared the argument. Does it make sense? Do you follow? This is basically the core idea. And then, since there is a return instruction in the gadget at the end, when the return instruction is executed, it reads value from the stack and jumps there, right? Because that's what we also learned in the theory, that return instruction is just a syntax sugar for pop rip, basically to read value from the stack and put it into instruction pointer. Return instruction just says jump to the value that is on the stack. Okay? All good? So now if you think about it, by chaining these gadgets behind each other and executing them one by one, we can actually program anything we want. Because the binary, there are millions of instructions in binaries nowadays. So we can just find the correct instructions, the correct gadgets, let's say, chain them together and program anything. This is the theoretical abstraction. Now we will actually get to it and try to execute it. Did it make sense so far? Question? No? Okay. So we will be using these gadgets, and we need to find the gadgets. In order to find them, we will use a tool that is called Ropper, that is already installed in the exploitation lab. So let's try to use it. Again, make sure you are still connected to the exploitation lab. I'm gonna go there, I'm gonna clear this. So first, you need to activate this Python virtual environment where the Ropper is installed. And now you can put to the Ropper basically any binary you want. In this case, I executed this command, which puts there a binary date. And in the output, you can see that you can see a list of gadgets. So, for example, this is one gadget, okay? 2 instruction gadget, and I have an address where the gadget is located, okay? And then I have many other gadgets. Here, for example, those look quite complex, but see, maybe you need some of those. Here, for example, I have 3 instruction gadget that just subtracts from stack pointer number 8, then it adds again to stack pointer number 8, so it's redundant, and then it returns. So this is the way how we can find gadgets in binaries, okay? We will use it in a while. Also, let me show you this command, because we can use the wrapper to find just a specific gadget. So for example, in our case, we want to prepare the argument of a function we will call in the first argument of a function we will call in a register, right? And the register is called RDY. So for sure, we will want to execute this instruction, pop RDY. So I can just say wrapper, hey, I'm looking for a gadget that contains this instruction. And look, I'm lucky, because in this example, in the binary called date, we found this gadget, which is exactly the one we needed, right? It just puts a value from the stack into the RDY register and returns. Okay? So this is the tooling that we will be using. And now let's move to the example. By the way, again, small disclaimer for the mock students. This example will not work at all for you if you are running it on ARM Mac processors. So sorry for that. But for those of you who have Intel computers, SEL should work flawlessly. So we will do a little hack. We will make it a little bit easier for us, because this would be quite advanced exploits. And we will actually disable the ASLR, okay? We will disable the randomization of the virtual address space. We will do it with this command. So please run it. And it will start for you a new bash that has ASLR disabled for all its children processes. Okay, so we will be working in this new bash. And now let's look at the code that we will be exploiting. Let's copy it again back to our home and go inside. Inside you can see 3 files. Again, there is a C source code that you can see in the document. Very simple one. And if you remember correctly, this is the exact source code that you saw during the motivation example in the beginning of the class, that I was showing you the magic Python script that spawned the shell from the echo program. So this is the echo program. This is one-to-one it, and we will now try to exploit it. So our goal is to spawn a shell that we did in the motivational example. We will spawn a shell by running this. Okay, imagine that this system call with a shell argument is in the code. We try to achieve this. So we are calling a function that accepts an argument. That's exactly the problem we are trying to solve. And we already are able to override the return address of the main function to any function we want. So we can jump to system. It's easy, right? We already did that in the previous example. But so far, this argument will not be set if we only jump to system function. So before we jump to system function, we need to actually put this argument into the register. Okay, do you all follow the plan? Thank you. So this is, again, diagram of how the stack will look like when we try to smash it. There is a local variable that has 64 bytes. It's the buffer. Then again, there is the old RBP value and the return address, which means we will try to override the buffer, override the RBP value, and override the return address with some gadgets that we create in a way to set up the argument in a register and jump to the system function afterwards. Okay? Okay, this is basically, I believe, what I just said in the document. You have it written there, the plan that we will try to do. And let's see this document that is pretty much showing exactly what I just said. On the left side, you can see the stack, what we want, how we want to smash the stack. Okay, this is after the user input is read. So you can see the start buffer. We overwrite it with any gibberish. We don't care. In this case, it's a letter A. So we put 64 letter A's. So we overwrite 64 bytes. Then we overwrite the old RBP value, which was there. So it's just 8 bytes. So we put 8 characters. Again, we don't really care what we put there. And then the magic starts. So this teal color was the original return address. Okay. Before we execute the system function, we need to prepare the argument in the register. So we need to execute this teal gadget that is actually popping value from the stack into the register. That is the first argument, okay? Basically, we will override the return address with address of this gadget. That's why there is the arrow, because it's a pointer. It's pointing somewhere where this gadget is. And in this case, you can see that we call it here libc, because that's our plan. We will try to find all these gadgets in a libc library that is already loaded by almost all C programs, okay? So if we successfully jump to this teal gadget, it will execute pop RDY. That means it will read the value from the stack and put it into the register. And the value on the stack should be our argument. That means the next value on the stack, we should put the address of the argument. In our case, that's the bin shell string, okay? That's the purple color. So the purple color, it's not actually a gadget. We are just pointing to some data that is bin shell. And we hope this bin shell string is already in the libc library. If not, it's going to be difficult for us. Right now, this is our plan. We hope that we can find it somewhere in the libc library. So these two, the teal color and the purple color, what it does, it sets up the argument in the register for us. And afterwards, we just put the green color, which is address of a system function. Because after this shell is popped into RDY here, we execute ret. And return address will use the green color to jump there. Okay, so we will jump to the system function while having the shell argument ready in the RDY register. Are you following? Who is not lost?
Be sure you understand, make questions. Gadgets are hard to get. This is the moment, people. Questions are fine.
Okay, so and now if we actually understand that this is the plan, and here in the left side, you can see basically how we want the stack to look like. So we can just write the exploit now and fill all these values, okay? And in order to do that, we have 3 tasks. Those are the 3 colors. So we need to find address of a system function in libc. Then we need to find address of the bin shell string somewhere in the libc. And then we need to find this pop RDY red gadget, which is the teal color. Okay, we have 3 tasks that we need to solve before we can write the exploit. So let's try to do that together. While we are trying to find these addresses, try to write them down or save them somewhere for you, because you will use them later to finish the exploit. So as I said, all these three addresses that we are looking for, we will be trying to find them in the libc library. Okay? So we need to find what libc library is our binary using. And we can do that again in GDB. So let's try that. Go into your directory. Don't forget to execute make to actually compile the binary. Now I load it into GDB. I put a breakpoint into the main function so that I can start the execution of the binary, but it stops the execution when it reaches main function. Okay? It's basically like a debugger. So after I put the breakpoint, I say run. It started running, and now you see we reached our breakpoint. So the binary is in the middle of execution. And now if I do infoproc map, oh, sorry, I will make it smaller. I hope you can still see it at least a little bit. Now we can see what shared libraries were loaded into the runtime. And we can see that we can see the libc over here. This is what we were looking for. So now we know that the libc library that is running there is this one. It's just a file in the system, right? You can see it's user lib, and it's living right here. And it's loaded into this address. Those are the two critical information for us to remember. If I go back in the document, you have it highlighted here on the screenshot, okay? So we found this address, that is where the libc is loaded, and we find what is the libc library. So let me copy this address. Oh, sorry. Let me quit GDB, make it bigger for you again. And I can go to the exploit template that you have there, and I'm gonna write it down, okay? So libc address is this one. That's what we have so far, okay? I'm gonna save it, and we can continue. So now, since we know what libc we are using, it's this one. This is just the copied string from the above screenshot. We can try to search for the system function in this libc library, okay? Because if you look at our plan over here, so first plan was to find the address of a system function. Sorry. Sorry. Here. Our first task is to find the address of a system function in libc. So we can use this command. Readelf is a tool that is for reading elf executables. And it gave me the offset, okay? It's this one, where the system function lives. So I can go back to our exploit and type it down. I can do that system address is actually at the address where libc is, right? Because it's living in the libc at this offset that we just found. And again, everything is in hexadecimal. Okay, so now we solved first task from the 3 tasks we had. Let me save it again. Second task we have is to find the bin shell string, again in the libc. We can, in this case, we can use a strings command that is used to discover strings in basically any binary file. So let's copy the command. And voila, this is kind of coincidence, but it's a happy coincidence for us because we tried maybe there is bin shell string in this binary, and it is, so it's nice and we can use it. If it was not, we would need to find some other way how to exploit this. But what we discovered is this number, which is where this string actually is in the binary. So again, let me copy this number, go back into the exploit file and write it down. And I can do that bin sh address is again in the libc address at this offset, what we just found. Okay. Let me save it, and we can continue with the final missing part, and that is the gadget. Here, let me go back to our plan. Our plan was to find address of a system function. We have it. Our plan was to find address of a bin shell string. We have it. And the last stuff we need, find a pop RDY and return gadget. Number 3. And we will use wrapper for that. You can use this command, which is basically saying, okay, so in this libc library, again, the same libc that we are using all the time, try to find some gadget that has this pop RDY instruction inside, okay? So let me not exploit it, but run it. Come on, come on. And right here in the below, I can see this is exactly what I wanted, right? I was searching for pop RDY and return, and I got this offset. So again, I just copy it, go back to the exploit, and type it down, that this is our pop RDY gadget. Again, living at the same libc library at this offset.
There is a question.
Yes?
Second. What are the other lines from the infoproc map output where the library is at some offset? Is it the library loaded, fragmented in memory? Do you know?
Yeah, I believe it's a table of loaded symbols, right? In the binary. Yeah. I'm not 100% sure in the terminology right now, but you would find definitely all the shared libraries that are loaded in the runtime, including other sections of the binary itself that you are running at the moment. Yeah. Okay.
It's also, you see that they have different permissions, some of the executables. So it's like the binaries that have the data and the constants and the different symbols in different places. So
yes.
Yeah.
Okay, so now since we have these 3 addresses, that was our plan, we can finish the exploit. Let me show you. Do I have here? Unfortunately not, but here, let me show. Sorry, I'm scrolling a little bit up to see this our plan. Okay, this was our plan. So we need to write 64 bytes something. Let's say letter A. So let's do buff. Let's do letter A 64 times. Then we need to write 8 bytes of something to override the old RBP. So let's do B 8 times. Sorry, I have a typo here. And now we are writing our addresses, okay? So first we need the pop RDY gadget. So I will edit again with the struct.pack so it handles the endianness for us. And then address of a bin shell string. And finally, the function where we want to jump, the address of a system function that we also have here, which is the system address. And this is all. So this is the exploit, at least in theory. So we are overwriting the local buffer, then we overwrite the old RBP, and then we put the chain of the gadgets that we planned. Okay, you don't need to write it on your own right now. What I just wrote down, you can find here in the document. Should be the same, except the gadgets addresses can be maybe a little bit different, because every time you run a wrapper, it can show you different address for the same gadgets, because there are a lot of same occurrences of the same gadgets, and it's each unique gadget printing only once, because otherwise it would be redundant. So it's not deterministic, the output, and sometimes you can find a different gadget, different address for one gadget in the output. So let's try to run this. Let me try to type something, and I got segfault. Fortunately, this is a nice segfault because I was expecting this. There is one more drawback. This is unfortunately not working, and it's again because of the alignment of the stack. Okay, the stack right now is not aligned to 16 bytes, as we said before that it must be when you are calling some function. The function that we called expected the stack to be aligned, but it was not because we broke it. Okay, so how to solve this? We need to put something more on the stack to align it. Do you have an idea how we could achieve this? What can we put on the stack to align it and keep the gadgets still working? We need like a NOP instruction, right? We need to put something, but we don't want anything else to happen because we have all the logic, all the logic is there. We just want to align the stack. So how could we do a NOP instruction? Any idea? Well, if you remember the question...
No, I want to offer candy. I have a lot of candy for the answer.
Yeah, candies. This is maybe even 2 candies. This is a difficult question. Could be chocolate.
Do you want it to be chocolate?
The cube.
Somebody took it. Oh, no.
Oh, it's gonna be bad. I broke it last year.
Are you ready? 1, 2, 3.
Nice.
So I guess we're looking for something that is effectively a NOP.
Yes.
But it still allows us to pop from the next value that's on the stack, right? So basically just a ret.
Well, yeah. I think you already said it, but basically, just to understand, this is what we did so far. This is how we smashed the stack. Right now, we need to add something more somewhere so the stack is aligned in the gadget section.
Yeah, so I'd expect just returning to something that will just return back.
Yes,
to then execute
exactly. Thank you. So that's what I was asking you before the second break, if you can think about what would happen if we actually override the return address with address of only return instruction. What would happen? Well, nothing, right? It would be weird because if you override the return address of a function with return instruction, what happens is that you execute return instruction, but return instruction just pops another value from the stack, jumps there, and continues. So it's effectively a NOP instruction. Does it make sense for you? I see some nodding. So let's try to find this NOP instruction. Again, just using, sorry, I'm scrolling unnecessarily, but here. So we are using the same wrapper command. We are just using search only for return, okay? Not pop RDY. Now we are interested only in some return instruction.
Is it clear that we are saying NOP, that no operation instruction, but we are not searching for NOP? It's like just something that does not make a change, right?
And here in the output, I'm looking, and here I see a simple gadget that is just a return instruction. So this is exactly what we were looking for. So I'm just gonna copy the offset, go back into our exploit, and add one more lib, which is NOP gadget, which is again living in libc shared library, and at this offset, okay? And let me put it into our chain of gadgets that we are with which we are smashing the stack, like this. And now the stack should be aligned, okay? We just added 8 bytes on the stack, which is effectively a NOP instruction, and the logic should be preserved. So let me try to exploit, to run it again. Well, I got shell. So this is the same example that I was showing in the beginning of the class, okay? Now this exploit.py Python script is the magic.py script that I didn't show you in the beginning of the class. So now you understand how we actually did it. Did any one of you succeed it? Nice, thank you. If it's not working for you, remember you need to disable ASLR with this command. So you can maybe if it's not working for you, try to execute it again and then try to run the exploit again. Just a small note at the end. You notice that we disabled ASLR. In production, when you want to actually exploit a real binary on a real system, ASLR won't be disabled, right? So it won't be this. This was quite difficult. And yet, in the production, it will be even more difficult because there will be ASLR. So how would you bypass the ASLR? Well, in ASLR, if ASLR was disabled, this would not be correct, okay? This value, we don't know where libc is loaded. So if ASLR was not disabled, you would only need to somehow find where the libc is loaded and discover this number. And if you get this number, you are able to exploit this binary on any system or on a system with ASLR. So it's still doable, just we are not doing it in this class. So this is all from the binary exploitation and return-oriented programming system. So you cannot like disable it for the whole operating system and for everyone. Fortunately or unfortunately, I don't know. Okay, so 5 minutes. Last section of this class was fuzzing. It is still fuzzing. Very briefly, just to tell you what it is and how it is actually related to what we just saw and the binary exploitation, because if you know about fuzzing, maybe you think that it's not really related, but fuzzing is a very nice technique. It's a testing technique that can reveal bugs that can lead to stack buffer overflows that we just exploited, okay? Fuzzing is a automated software testing technique, and it's automatically producing inputs for whatever targets that are accepting inputs, okay? Just so you observe the behavior of the system. So you can imagine applications, maybe even those we just saw. You can randomly create input, put it into binary, and check if you get segmentation fault. Maybe you do, maybe you don't. If you don't, that's good. If you do, that means there is a bug that can be maybe exploited with some of the techniques that we just saw. Let me just very fastly try to show you. So for example, you can try to fuzz very naively, very easily, with only completely random inputs that you can get from dev urandom device in a Unix system that is producing random bytes. So if I do this part of the command, I just read urandom and take 100 bytes. See, I always get something, gibberish. Random bytes, it's not even ASCII readable. But let's try to feed it into the binary that we had in the first example. Just 100 random bytes. Oh, see, access denied, access granted, access granted, access granted, access denied. So even with this very naive technique, I can observe that there is very different behavior for each different input. How is it happening in this case? Is that because the binary is reading the input until the first new line. But where the new line is in this random input, it's random, right? Maybe it's at the 100 characters, maybe it's in the 5th character. It's always triggers different behavior in the binary, which is the goal of fuzzing. You are trying to generate random or pseudo-random or somehow smartly random inputs that you feed into whatever that accepts inputs, such as compilers, applications, whatever, and observe if it breaks or not. We have other tools mentioned in this section. I'm going to skip them. Feel free to look at them after the class. You can try to run them with the commands in the document. They are nice and quite useful. I would also like to say that recently there has been some progress with fuzzing because of the latest AI progress. And the main reason is that the LLMs nowadays, they are quite good in generating not really completely random output, but a structured output, right? So imagine that before you wanted to fuzz a compiler, and compiler accepts source code. Source code is not completely random. If you generate random bytes, the compiler will not accept it, right? So you need to generate a good enough source code, but still so it's random and it's something humans would not think of. So LLMs for this are extremely good, right? Because they are able to generate you any kind of structured output that you can use as input to, for example, fuzz even compilers that you would not otherwise fuzz, because how do you generate the input for compilers? You would use the same state machine implementation as is in the compiler, but that's not thinking out of the box. And yes, so we approach till the end. Announcement for the next class, which I already mentioned, is going to be about reverse engineering. It's going to be with Mari. So please, all of you, both CTU students and online people, make sure you have Wireshark installed on your computer, on your host computer, and also download and install IDA. Free version on your computer that you will be using to reverse engineer binaries and programs. Good news is there is, again, no assignment this week for you guys.
Ooh.
So you can try some challenges in SCL or catch up with the other assignments. And also a heads up that this is maybe a final chance for you guys, and mostly for the online people, to vote for the topic of the last class with a postcard, okay? Because we need to accept the postcards no later than 11 December, I believe, which is less than a month. So if you want to vote, and we encourage you to vote, please do so as early as possible. Also, please fill the feedback. I'm going to read it. Even if I cannot change this lecture, but I'm going to read it and update the lecture maybe for next year. So please fill the feedback. And yes, that's it. You guys.
Remember, please, the postcards that we are waiting for you. Go and vote. Remember, everything is on the webpage. Remember, please, the feedback. Veronica was saying that less than 8% of the people is giving feedback. This is your opportunity to get better or worse the class, so you can tell us what you think, please. Even if you like it, we really go line by line. And remember, next class is not going to be in this room. It's going to be in
301.
301, and then we are back here, okay? Online is going to be the same link, the same video, the same document, everything for you, okay? Something more we are missing? Questions? You want to go back to the gadgets again? We can. Okay, so see you next week, people, and thank you very much for coming.
Thank you, and see ya.